Calibration curves is the first video in external and internal calibration, which is the topic for today. So after watching this video on calibration curves, you should be able to plot a calibration curve and a line of best fit, use a calibration curve to determine the concentration and estimate error associated with the concentration of an unknown, and also design and execute an experiment making proper use of calibration curves.
So, basically, you take a bunch of data where you make a solution where you know what the concentration is, or you know something about it, and then you measure the instrument response to each of the solutions that you make. So then you take this data and you fit it to a line. With the equation y equals mx plus b, where m is the slope. And so for each, in order to do this, you have to make a couple of assumptions in the data treatment. And we're not going to go into the math behind all of this, but basically the variation in x is less than the variation in y, which is actually a pretty good assumption because you made this solution. You should know what the concentration is pretty well. And so what you should be measuring is the error associated with the instrument response at each concentration. It also assumes that the error associated with y is similar for all measurements, and that should be correct because obviously there's error associated with these measurements if you measure them more than once, and I would recommend measuring them at least 3 times because then you can do a standard deviation on each point. And so it's assuming that these errors are similar for all points because, and it should be, because if your instrument response is relatively similar over the range that you're measuring, then the errors should be the same because you made your solutions.
Here's another example from your book of a calibration curve where you have on the x-axis, the horizontal axis, the amount of protein, and on the y-axis you have the instrument response. So you can fit this with a line y equals mx plus b as shown in the slide.
The math behind this is called least squares fitting, and essentially the method is that you're trying to minimize the distance between each point and the line. And so you square it because there's got to be a point below the line and a point above the line, and so in order to have to deal with the negatives, you just square it. So basically di squared, so the distance between each value in y and the line, you basically have that y value minus y from the equation of the line squared. And so that since y equals mx plus b, you have yi minus mxi plus or minus b squared. And so the whole point of this entire math, it's a bunch of matrix math, is that it minimizes the sum of the distance in y between the point, all of the points, and the line of best fit. And that's how you come up with the line of best fit. So the error associated with these y measurements is calculated by the sum of the deviations minus d bar, which should be 0 because the average distance from each point to the line should be 0 once you sum it over all of the points, over the degrees of freedom. And so d bar should be 0. Degrees of freedom is likely to be n minus 2, and we'll talk about a little bit more about degrees of freedom in a minute. So the error, sy, should be the square root of the sum of di squared over n.
As you can see from the graph, least squares fitting is used to minimize the differences between the line of best fit and the y values. You can also see the least squares line of best fit equations for slope and intercept, and also how to calculate d, which is used in calculating error associated with a calibration curve, the unknown concentration that you would calculate from a calibration curve.
So the last thing I want to talk to you about is calculating the uncertainty associated with the concentration when you measure the unknown absorbance and then you come down and you find the concentration from your calibration curve. How do you calculate an error associated with that? And since we're in the statistics and data treatment portion of this class, it's all about quantifying error. And so here it is. Here's the equation. S of x equals S of y over the absolute value of the slope, and then times the square root of 1 over k, which is the number of measurements of each unknown, which the replicates, plus 1 over n, which is the number of points in the calibration curve, plus y, the measured y value, minus y bar squared, quantity squared, over m squared, slope squared, sum of xi minus x bar squared. Yeah.
Here's the equations that you'll need to estimate the error associated with an unknown concentration as measured by a calibration curve.
Degrees of freedom is essentially the number of independent observations. So say here, each of these x's is an independent observation. There's 7. So the degrees of 7, if you don't need any other data. So the degrees of freedom is reduced by the number of values that you need, or the number of other pieces of data that you need to go into the formula. So, for instance, that sounds a little bit nebulous, but for instance, you have a degrees of freedom of n minus 1 for a standard deviation normally, because in order to calculate s, you need x bar. So in this case, the degrees of freedom is n minus 2, because in order to calculate sy, you need to calculate both m and b, which takes away some of your degrees of freedom. So what we talked about is a little bit nebulous, and I'd like to make it a bit more concrete by talking about an actual experiment that you're going to be doing in Lab 2. So that is using a UV-Vis spectrometer, and basically, I'm not going to go into a whole lot of detail right now, but essentially you have a source, which is basically a white light, many wavelengths coming in. It interacts with the sample, and then you have fewer photons at fewer wavelengths coming out of the sample. And so then you use a monochromator to disperse it into its component wavelengths, and then the detector detects at a bunch of different wavelengths. So essentially you have sort of an instrument response curve that may or may not be flat, but we're just going to assume it's sort of flattish. And then once it passes, that's before you get to the sample, and then after you've come through the sample, you see that there's this big divot where all the photons of a certain wavelength got absorbed. And so that's essentially a UV-Vis experiment. And so you often use a calibration curve, actually I think always, use a calibration curve when you're doing a UV-Vis experiment. So let's talk about constructing a calibration curve. The first thing you need to do is prepare and measure your standards and your blanks. Then you subtract your blank values from each of your measurements. That's called the corrected absorbance. And then the third thing you do is make a graph and determine the slope, intercept, and errors. So now we can put labels other than x and y on these axes. You make a bunch of different solutions at different concentrations of whatever you're measuring, and then you measure the absorbance. And so you come up with an equation of absorbance equals the molar absorptivity times the path length, which is basically m, times the concentration of whatever you're looking at, x, plus b. And b should be 0 because when there's no analyte in the solution, you should have zero absorbance. So then when you have an unknown, you just measure the absorbance, come right across on the graph, and find the concentration. So, alright, the next thing is that you want to use at least 6 standards in order to have good statistics and be really confident that nothing's wrong with any of the points on your calibration curve. You want to do at least 2 measurements of each unknown, and it would be preferable to do 3 or more, because if you have 3, then you can calculate a standard deviation. Alright, avoid serial dilutions. If something's wrong with your stock solution, and you use that to sort of perpetuate and make all of the subsequent serial dilutions, that's going to be a problem. And then the last thing that they suggest is that you measure standards in a random order so that you don't have drift. And I actually like to do sort of a bizarre, or like a little bit different version of this, in that I like to measure my standards in order from least to most concentrated, and then I measure some unknowns, or I might go back and measure a blank, and then I measure my standards as unknowns afterwards to see if there was any drift associated with the measurement, or with the instrument. See if it's drifted around.
Go ahead and test yourself by doing this problem from your book.